Okay, so Newton's second law of motion states that the acceleration of a body A is directly proportional to the net force acting on it, and is also proportional to its mass. So the way we normally represent Newton's second law is F equals ma. And you can see in our booklet, we've also got sigma F equals ma. Here, this means that we've added all the forces. You don't need to worry too much about the sigma there, because for your examples, you mainly have just one force acting on the object. You could potentially have friction acting in the opposite direction, but you're not going to have like the three forces that I had up before. You won't have really complex examples. So what we're talking about though is that we have to think about all the forces that are acting on the object, and we can work out the force if we know the mass and acceleration, or we can calculate masses if we know the force and the acceleration. We can work out the acceleration from the force and mass. Okay, they're all interrelated. Note that this is mass. Okay, remember, what's mass measured in?
Newtons. No, kilograms.
Kilograms. What's acceleration measured in?
Meters per second squared.
And what's force measured in? What's the units for force?
Newtons.
Yeah, newtons. So force. So 1 Newton is equal to 1 kilograms meters per second squared. But this is how we express our answers, is for forces in newtons. But you can see where it's derived from this relationship here. And we can often think about Newton's first law as just a special case of Newton's second law. Because if we have no acceleration, then we're going to have no force. Okay? So this is what's happening, is if we've got no acceleration in Newton's first law for objects that are stationary or moving with a constant velocity, then there is no net force. Okay, so that's why Newton's first law is a special case of Newton's second law. But let's have a look to see, well, how are questions frequently presented for Newton's second law. And we've got an example on page 51, worked example 18. We're asked to determine the size of the force. So we want to find the force, and the mass is 80 kilograms. The athlete weighs 80 kilograms, and we want to find out the force, but they are accelerated from rest to 12 meters a second in 5 seconds. So we know the initial velocity is 0. We know the final velocity is 12 meters a second, and we know that this took place over 5 seconds. So we can use our equations of motion relationship here to find acceleration, because we know that v is equal to u plus at. So A will equal V minus U on T. That allows us to find A, because we want to use that. We need acceleration for our calculation over here. I can just substitute this relationship directly into this formula. And then I can do one calculation to find the, so my final velocity is 12, my initial velocity is 0, to find the force, 192 newtons. Now, we should still have direction because force is a vector. So we weren't given a direction, we're just going to say in forward direction or positive direction. And so let's have a look at worked example 19 as well. It says here, a freestyle swimmer whose mass is 75 kilos. So we've got mass is equal to 75 kilograms. Applies a force of 350 newtons. As she begins the race. The water opposes her efforts to accelerate with a drag force of 200 newtons. So the drag force, if I've said that the swimmer's force is in the positive direction, what's the direction for the drag force? Negative. So it's going to be minus 200 newtons. What is her initial acceleration? Well, what we need to find out is the net force. And the net force is just the sum of all of the forces acting on this object. And so the net force is equal to 350 plus minus 200 newtons. Okay, we always add forces together, but this one happens to be a negative force acting in the negative direction. That's going to give me a net force of 150 newtons in the positive direction. Now we can use F equals ma to find acceleration. A is going to equal, acceleration will equal the force divided by the mass. So my acceleration is equal to 150 divided by 75. That's going to be 2 meters per second squared forwards. Okay, because, so that's in the direction that the person is swimming. I spoke to you before about weight, and weight is a force. And the weight force is equal to mass times gravity. So this is gravity, or acceleration due to gravity. What else do I want to say about Newton's second law? I think we'll have a look a bit more at this relationship here. There's quite a number of questions that focus on this, and they do this by saying what's going to happen to the force if T increases.
Become less.
It will. The force will decrease. And this is the reason why like pitchers and wicket keepers, baseball pitchers and wicket keepers in cricket, wear padded gloves. The padding is going to increase the time it takes for them to catch the ball. Okay, the ball slows down because of the padding. And the other thing wicket keepers do is they move their hands backwards with the ball as they're catching it. They're doing that, again, to increase the time. The longer it takes them to catch the ball, the smaller the force that's hitting their hands. Okay, if they don't do that, they might end up with broken bones in their hands. Okay, because they're going to have the full force of the ball hit their hand. So the same, just say there's a fire on the ground floor of a building and people are expected to jump out of the building, otherwise, you know, they might die, for example. You compare jumping out of the building onto concrete with maybe jumping out and going through bushes, or you know, there might be an awning, or there might even be somebody there with, like there might be mattresses on the ground. You know, like as in, or you know, those cartoons of the firemen rescuing people with the, you know, with a trampoline, that sort of thing, like a rubber mat that they're going to catch people with. What is the function of that? It is to increase the time of the impact, because the longer it takes, the smaller the force. You jump out of the first floor building onto concrete, you're going to break bones. Okay? You're going to have the full force of that impact. But if you can slow it down, then you're going to, the force will be smaller. Now, if we think about that person jumping out of the burning building, when they hit the ground, just say here we've got some mattresses, and there's some fluffy pillows here for them as well. The force is smaller for them, but is the force what's going to happen with the force on the ground? If we say that we've increased the time of impact, and that's lowered the force, so they're not going to break their legs. What about the ground though? What's the size of the force back up from the ground?
The equal force to that of what was the impact. Like it'll push up with the same amount of force as what the person applies to it.
Yes, that's right. Why? Why will it be the same?
It's like the whiteboard, you're not going to push the whiteboard down, you're not going to push the ground over.
Yeah, so the force is equal in size but opposite in equal in magnitude and opposite direction. But if we reduce the force on the person, we're reducing the force on the ground as well. Okay, because it's, yes, when we have that impact, it's going to be the same for both objects involved in that impact. All right, so That's why it's a good idea to wear gloves if you're playing cricket, and it's a good idea if you're jumping out of a building to try and land on something soft. So you're going to increase that time and reduce the force. Alrighty, I'll let you get back on with your questions.